Hi, everybody. All right, another online class. This is Hydrologic Engineering class number 37 for Friday, the 15th of April. Just some announcements. First of all, the class that we're going to have on Wednesday of next week will be in the hydraulics lab rather than our normal classroom location. And the reason for that is that there's a research conference being held in the building, and they've appropriated our classroom for that. So we're going to move our location over to the hydraulics lab for Wednesday's class. And then next Friday, a week from today, that class meeting will also be online, like today's class lecture is. And then finally, the last announcement is that homework 12, which is two problems, one related to flood control and one related to groundwater and wells, that assignment should be uploaded to Blackboard before 5 o'clock on Friday, April 22nd. Today's class meeting, we're going to continue the discussion of flood control and some structural measures for controlling floods and trying to reduce the impact and damage that they're able to cause when flooding occurs.
Okay, levees and flood walls are different because it affects all three of those curves. So let's look at them individually. The damage versus stage, the way it works there is that it's saying that you're not going to have any damage until the water gets to a certain depth. And so here's a picture of a levee, and you can see that there are homes that are built below the water level. Now, they're not going to have any flooding until the depth gets above the edge of the levee. But then when the water does get above the levee, then all of that damage comes in suddenly. And so they've got this initial failure where the water's just starting to slowly go over the edge of the levee, but then when it gets a little bit higher, what they're saying is you instantly get up to all of the damage level that you would have had, because all of the areas that are low-lying are going to be filled with water once that levee fails. And so, how are you protecting the people? Well, number one, the depth versus damage relationship has changed. Now, the thing that's interesting is that what a levee does is it makes the discharge versus stage curve a little bit worse than it would have been. And so this is saying for a certain flow rate, the depth is actually higher than if the levee hadn't been there. And that's because you're confining the flow into a narrower area. Then, a levee is essentially you're putting a wall on the side of a river. And so you're making it so that the water depth, here's our river, you're putting a wall up so that the water is now up to this level, whereas it would have, if the levee wasn't there for a certain flow rate, the water level wouldn't have gotten so high. So you're kind of confining the width of the flow. And so what that says is that the discharge stage curve is above the original discharge stage curve, and that's considered not good. It would have been better if, for a certain flow rate, the depth was lower. And the same thing is true with the exceedance frequency versus discharge. That's higher, which is worse, because by putting up those walls, you're increasing the flow velocity, because you're kind of forcing more of the flow to be in contact with less of the wetted perimeter, and so you're going to be having you're increasing the flow capacity of the stream. And so for a certain flow rate, the discharge could be higher. For a certain size storm, the discharge is going to be higher. It increases the speed of the water's travel, and so it's all concentrating a lot more fast. So the levee does one good thing and two bad things. Now the net effect is positive because hopefully we're only having a small increase in the discharge, only having a small increase in the stage, and you're protecting all of the area surrounding the levee. Does anybody have any questions about the levee and flood wall? Yeah, Austin?
Would it be more beneficial to kind of match the slope of the side of your channel and extend it up to like the curve of the levee levee as opposed to just putting a flood wall in that restricts the width. That way you still have your width, but you still
Yeah,
have that
yeah.
barrier.
I mean, the wider, this is not to scale, but yeah, I mean, in reality, I think, you know, like the floodplain may have several different steps to it. And they probably, your point is you want to make the channel as wide as possible. Like you wouldn't build the floodway, you wouldn't build it here, but you know, the wider you can make the channel, the better, yeah. So they want to maximize the capacity, but you know, the wider you make the levee, the less land you have for development. And so I think what they're trying to do, you know, like in the Netherlands, for example, is balance how much land they want to reclaim versus how much flow carrying capacity they need in the levee. Here's a picture of Huntington's flood wall. You know, they occasionally, I think just within the last year, they put the doors in there at the Riverfront Park. Here's a picture of the water up to the flood wall. Channel modifications is another one of the structural measures, and you can see this is a crane that's doing some dredging work in the channel. By straightening out a channel, you increase its flow carrying capacity compared to if it was meandering. And so what channel modifications allow you to do is they allow you to, for a certain flow rate, the stage is going to be lower than it was before. Like if you're excavating the soil at the bottom of the stream, you're lowering the water level because the bottom of the channel is lower than it used to be if you're doing dredging. Or if you're making the stream more narrow, you're increasing the hydraulic capacity of the channel. So for a certain flow rate, the stage will be lower. And so that's where the value is. This is the good thing that you're doing with the channel. And so, you know, if your stage is lower, then that means for a certain storm, there's going to be less damage. On the other hand, the negative thing that it does is it increases the amount of discharge that you're going to see for a certain exceedance frequency because the water's making its way through the channel more quickly. And so it's kind of like increasing the peakiness of the channel because the water can move faster. So you're decreasing the local storage inside the stream. Like if you have a meandering stream, a greater volume of water is in the stream itself than if it's a straight line connecting 2 points. And so you're storing less water in the channel, but the positive is that the depth is lower. So that's the improvement that it makes. Flood-proofing, non-structural measures like waterproofing the walls or raising a structure in place or flood warning systems that can allow people to evacuate and move their vehicles, those sorts of things, what it does is it makes it so that you have to have a higher depth of water to get a certain amount of damage. So all of these non-structural measures aren't changing the watershed, it's not changing the channel, but instead, and those are what we think of the structural side of things. The non-structural measures are affecting the damage-stage relationship. And so it's saying that you'd have to have an even greater depth of water to get the same amount of damage that you had before. Okay, we've got just a couple of minutes, and so let's take a quick look at the water.weather.gov website. I wanted to show you that here under the Water tab, this is weather.gov and the Water tab, it allows you to zoom in, and let's see if we can find the gauging station for the Ohio River at Huntington. Okay. Getting close. There it is. All right. So here's the, when I was hovering on it, it was bringing it up. Let's see if it'll give it to us again. Okay. So over on the right side, it's popping up the stage over the last couple of days. You can see that water levels have been relatively consistent, but they're predicting that the water levels are going to decrease. So I guess they're combining weather forecasts and hydrologic models. So it makes the river depth data available. Okay, yeah, I guess you got to double click on it. And then it has a lot of historic data here as well. So I guess we don't have any in recent history, any really notable storms. I don't know, did anybody live around here in 97? Remember a storm, a flood then? Yeah. So I think the flood wall that I was remembering, they had to put the gates in earlier this spring. So it looks like that was maybe around February 19th. It got up to 53 feet. So, and that's fairly high, but they have these different flood categories that classify, I guess a 53 would just be considered flood stage where they're having to put in the flood walls, but I don't think that it's really up to any particular height on the concrete flood wall. The other thing I wanted to point out on this water.weather.gov is there is the, let's go back again, river observations, and then there's also precipitation data here too. There's a precipitation tab where it gives you totals over the last 24 hours, and we can also go down here and have it change to like the last 7 days. And so you can see in the last 7 days here in the Huntington area, we're around, I guess, less than an inch of precipitation last 30 days. So kind of interesting. You can download the actual data for specific rain gauge, of course, but this shows you over a wider area how the precipitation patterns have changed. So if you know that your watershed is in a certain place, then you can look and see, like, remember the antecedent moisture condition. If you wanted to find out in the last 7 days how much precipitation there's been, then you could use this to model that. Let's take a look at the Map Service Center that FEMA makes available for floodplain mapping. It allows you to generate some PDFs that are pretty interesting, where you put in an address and then it'll generate an assessment of the risk of flooding at that address. And so anybody want to give me an address, maybe your aunt and uncle or your grandparents, or here in Huntington itself is kind of boring because of the flood wall. So I wouldn't ask for your address if you live in this area, but all right. Yeah, that's a good one. All right. So you can see what it's doing is it is breaking this up into areas where it's the floodway, so close to the river. That's where they expect during a 100-year storm, the water is going to be completely inundating not only the floodway, but then you can see that there are other areas where they're designating here in the hashed kind of tannish color where there's a 0.2 annual chance of flooding. And then the areas that are shaded in blue represent where during the 100-year storm it's going to be inundated. Now the PDFs that you can generate, all right, so let's do dynamic map. Hopefully this will load. It's creating what's called a firmette. And the firmette is a PDF that you can save that has all of the definitions built into it. It's got the location. So here's the address that's identified, the key, and if we wanted to print that, then we could make a PDF out of it. So that is how you generate a firm. And on the assignment, I ask you to to look up a couple of addresses in Milton and try and understand how they're different. You know, they're kind of varying proximity to the river in Milton and have different levels of threat assessment. Now, what I had to remove from this list of websites, in the past, FEMA had really easy access to the flood insurance rates, where it was pretty simple to calculate what the flood insurance premiums were going to be for a certain classification. But they've taken that off of the FEMA website, and now if you want to know what the flood insurance rates are, you have to get a quote from some of the, I think they have servicing companies that actually collect the premiums and process any sort of claims. But the premiums can vary quite a lot, where a home that is outside of an area that's designated as flood prone, and so here in these unshaded areas, the flood premiums could be, maybe $500 a year, whereas if you're living in these areas that are flood prone, the premiums could be $4,000 a year. I mean, it's really about an order of magnitude to live in the area that is inside of the 100-year floodplain versus outside of the 100-year floodplain. So it's kind of interesting how much it changes. All right, so that map service center is something that you're going to have to use for the assignment. This picture of flooding is from in Louisiana after Hurricane Katrina, and it shows just a bunch of wrecked vehicles, a muddy sidewalk, muddy yards, and one of the problems that they had with the flooding in Hurricane Katrina was that there are a lot of toxic tailing ponds from the chemical industry in Louisiana along the coastline. There's a big oil and gas and chemical industry on the coast, and a lot of those waste ponds got washed inland and spread out over a pretty wide area. And so it wasn't just the water affecting drywall and ruined carpets that was an issue, but there was a kind of like a secondary damage in the form of all this toxic waste that now had to be identified and cleaned up. And so what this picture illustrates is the range of different categories of harm people can suffer when there's flooding. When a flood like this has occurred, then people are going to be less interested in this neighborhood because now it's known as being flood prone. And so that can lead to like a reduction in property values, and it can decrease the amount of property tax that the municipality is able to collect on people in this area if the base property values decrease as well. So the book identifies a couple of different damage categories, and direct damage is the one that's the easiest to think of. It's the damage that's caused by the water itself and the cost of repairing things that have been directly affected by the flooding. But these other cost categories of damage are a little bit more abstract, and so if you think about the business revenue that's lost while things are either shut down or underwater, or while things are being repaired, businesses aren't selling gasoline, they're not selling hamburgers. And I remember driving through the floods that they had in West Virginia back in 2016. I drove through a town that's really close to the Greenbrier. Was it Sulphur Springs? Yeah, I was driving home from DC, and I knew there was a flood, but I didn't know like the whole town was basically evacuated because we were just looking for something to eat, and we drove into White Sulphur Springs and just nothing was open at all. And so, that lost business revenue is the indirect damage of the flood, where even if someone was up on the hillside and didn't have any water damage, then they're still affected by the fact that everyone else is either evacuated or the lack of access. Secondary damage is the adverse effects of people who depend on output from a certain area. And so you may know Alcon on Route 2. It's on the left side as you're driving northbound on Route 2. And so that's adjacent to the Ohio River. So if the Ohio River got really high and Alcon was flooded, then people who depend on whatever's happening there at Alcon, they make interocular lenses there. And so I think those are like replacement lenses that go into people's eyes during surgery. And so if there happened to be some sort of a global shortage on interocular lenses because of flooding in that location, then the people who can't get what they need would be experiencing secondary damage. And so we all experience secondary damage when there's a hurricane or flooding on the Gulf Coast because the cost of fuel goes up. And there are these periodic spikes after a hurricane or after a refinery disaster. But, I mean, you can detect that there are effects due to flooding. The cost of plywall and building materials can go up when there's a lot of flooding and damage in coastal areas, and so now suddenly there's a big demand, so the supply in other places decreases, and so prices can go up. And so that's an illustration of the types of secondary damage that can arise from flood damage, where you're thinking, well, thank goodness I didn't live in the flood zone, my house is safe, but still, you know, you've got a few dollars that you're having to pay because of the secondary damage that can occur. Intangible damage is the damage that's difficult to quantify on a dollar basis. You know, these are the disbenefits where an area is muddy and smells bad after a flood. Or it could be the social well-being that's lost. You know, people couldn't go to the baseball games that they were expecting to because now they're just shoveling mud for days at a time. The reduction in aesthetic value with driving through White Sulphur Springs after the flood, it wasn't as nice a place probably as it was before the flood. And so that reduction in the previous aesthetic quality of an area is classified as intangible damage because it's tough to put a dollar value on all of that. But then you'd think after all of these previous categories we would have exhausted all the different ways that flooding can cause damage, but there's also the uncertainty where businesses will intentionally avoid areas that are under a threat of flooding. Or if there's been a flood, then people are less willing to build there in the future. And it also limits the economic development. And so if you think about one of the reasons why West Virginia is kind of like chronically poor compared to the rest of the United States, you remember that we read that article that was saying that rivers and the overlying river and agricultural networks in the United States is part of what makes America perpetually rich. And so West Virginia is poor in both of those things. It's poor in flat land where agricultural crops can grow, and what limited flat land is available in a lot of places is immediately adjacent to streams. And so there's not going to be a lot of development in areas that are flood prone, and then everything else is like 45% slopes that's really tough to put a crop onto. And so you could say that there's some uncertainty damage that we face here in the state because a lot of the areas, we're lucky to have some flood control structure where there's dams that help to eliminate the risk of flooding, but there are still plenty of places that are affected when there's flooding. And so there's a failure to develop economically because of that uncertainty. Okay, so remember these relationships, these models that we talked about last time. And for each of these models, you need to think about what goes into the model, so the independent variable, and what comes out of the model. And so what we're going to have is the independent variable will be on the horizontal axis, and the dependent variable will be on the vertical axis. And so a hydrologic model is going to allow us to put in some return period, or in other words, an exceedance frequency, and then the curve or the sloped line, or maybe it's a flat line, but basically we bounce off of that and get a certain flow rate. And so you could prepare this curve by running WMS and a HEC1 model or a TR55 model. You could do it for the 2-year, the 5-year, the 10-year, the 25, and then you could make a curve that connects all of those flow rates. And so you'd have a different number of return periods, and then you'd have all these flow rates, and so now you've got a model that connects the discharge versus return period. And so what comes out of that is the flow rate. And then you take that flow rate and you put it into another model, the hydraulic model. And the way that you'd create this curve is you'd take a program like HEC-RAS, or you could do the calculations manually. You remember at the end of hydraulic engineering last semester, what we were doing was we were doing open channel calculations like the numerical integration method, the standard step method, where you were taking a known depth at a certain location and you were working upstream by looking at the slope of the energy grade line, the channel slope, and so you knew at a certain distance upstream what's going to be the depth for a flow rate. And so this curve is just for a flow rate, how deep is the water? and you run it for a lot of different flow rates. And so essentially, you know for the 2-year storm, how deep will the water be, because the hydrologic model told you the discharge, and the hydraulic model told you the depth. So we essentially know how deep the water will be, how often. You know, maybe once every 10 years, the water depth will be 10 feet. Once every 50 years, the water depth will be 12 feet. And then this final model, we put in for a certain depth, how much damage do we experience? And so stage versus damage. The input, the independent variable is the depth, and then this economic model, a surveyor has gone out and identified, you know, at what elevation are different structures. And then we have from the tax data the appraised value of every structure. And so you know if the water level gets to a certain depth, how many of the structures in a given region are going to be underwater from that survey. And then the economic data comes from maybe the assessor's office. And so we can know every 2 years how much property is underwater. Every 5 years, how much property is underwater. Every 10 years, how much damage is there going to be due to flooding. So the method that we're going to go through today as an example is we're going to calculate for different structural measures how much of that damage can be reduced. You know, if we have this baseline understanding of the amount of damage we're going to experience and how often we're going to have that damage, then different structural measures like dikes, levees, diversions, reservoirs, those things have a different amount of protection. And so we'll calculate how much reduction in damage each one of them provides. And then we'll calculate the annualized damage savings. And that's what makes this a little bit tricky, is there's some probability involved in trying to take an event that's only going to happen once every 10 years, and you're trying to spread the cost of that event over every year. And you may remember from engineering economy that you can have some cost that's a known present value, and you can find an annual value from that. Do you remember the time value of money calculations where you have some given P? So if P is given and you want to know A, then there are tables where you can find A given P for some interest rate and for N number of years. Maybe you remember that. Maybe you'll learn it again as you prepare for the FE exam. But what we'll do is we'll annualize the damage savings. And so rather than saying, you know, if we put in the diversion, it's going to prevent the 10-year storm. And so rather than taking that savings only one time in a 10-year period, you say, well, what's the annual value of that savings? Because it's damage that didn't occur. And so the benefit is experienced every year. It's not just experienced once every 10 years, because you don't know exactly right now, you don't know when that 10-year storm was going to come. Now, to go through that process of calculating the annual damage savings, we have to consider the incremental probability, which I think is best explained once we're actually looking at the example. But the idea is incremental probability is how much probability is there between the 2-year storm, for instance, and the 5-year storm. You know, the 2-year storm, in any given year, there's a 50% chance. The 5-year storm, in any given year, there's a 20% chance. So between those two, there's 30% of probability between the 50% chance and the 20% chance. And so the incremental probability is looking at the area under a probability curve. It's pretty abstract, but it'll make more sense as we're actually crunching the numbers. The damage reduction is looking at whether you can build a small diversion or a big diversion, which is to say, you could build a diversion that provides protection against the 10-year storm, or you could build a really big diversion that provides protection against the 25-year storm. And so not only are we comparing different alternatives, but we can also compare different sizes of alternatives, because everything's going to have a different cost. You know, the larger diversion is going to cost more than the small one. And so one of the example questions we're going to look at today is how to know how big to build something. And so to do that, you're going to look at the damage reduction that's saved when you go from preventing the 5-year storm and now preventing the 10-year storm, for example. So that's what the delta D is going to be. And then the annual expected flood reduction, what it does is it says there is a certain amount of damage that's avoided every year and a certain probability that that storm was going to happen. And so you combine it all together. You know, there was a 10% chance that this was going to happen and a 20% chance that that was going to happen, and you add up all of the things that were prevented. You know, if you're building to the 25-year storm, you're protecting against the 25-year storm, so you now can avoid the damage of the 2. You're avoiding the damage of the 5, the 10, everything below in size, below and including the 25 has been avoided. And so you get to kind of accumulate all of those probabilities and all of the costs. Okay, there is an Excel file on MU Online. It's a starting file, just so that you don't have to type all of the spreadsheet in from scratch. So go to MU Online and download that Excel file, and we'll work through it together to illustrate this example. It's at the bottom of the front page. Okay. So let's look at the data that we're given to begin this example. We have exceedance probabilities which correspond to storms of different sizes. And so, for example, a 20% exceedance probability, that goes along with the 5-year storm, because that means in any given year there's a 20% chance that you'll experience the 5-year storm. The 10% probability, that goes along with the 10-year storm, because in any given year there's not only a 20% chance of the 5-year storm, but there's also a 10% chance of the 10-year storm. So we are exposed to all of the probabilities cumulatively. There are threats coming from every direction. The existing condition is this is how much damage we experience in millions of dollars for a storm of a certain size. So you can see that the 5-year storm causes no damage right now. But the 10-year storm, if it occurs, we're going to have $6 million of damage. If the, let's see, 5%, that would go along with the 20-year storm, right? Yeah, 20-year storm. So if there's a 20-year storm, then that will cost us $13 million of damage, and so on and so forth. Now, one of the things that we don't see immediately is you think about like the 1,000-year storm. So that 0.1 exceedance probability, that's the 1,000-year storm. Well, $54 million is a lot, but there's only a 1 in 1,000 chance that's going to happen. And so actually, on an annual basis, the threat of that 1,000-year storm is pretty small, because the risk is spread out over 1,000 years. So when we go through these calculations, what we're going to see is it's not these really rare big events that threaten us the most on an annual basis. When you're adding up the annualized cost of damage, it's kind of these smaller and middle range storms that are providing the most risk. Because, in other words, I'd rather have a 7%, like think of it, what if you were going to win the lottery? I'd rather have a 7% chance at $10 million than a 0.1% chance of $54 million. So if you're going to look at the damage per event, we'll see that it's not these huge events that give us the most trouble. All right, so now consider there's 4 structural alternatives that are being selected, or considered. There's the dike, and the way the dike is working is that if it's in place, we don't experience the 10-year storm, and then we also don't experience this 7% storm, 7% probability. But then any storm bigger than that, it's as though the dike was never there. So we experience the full brunt of the storm for anything larger than the 7% probability. But then some of these others change the relationship slightly, like the diversion. Not only do you, with the diversion, you prevent more of the storms, like you're only seeing any damage at the 5% probability, but now it's also less damage. Instead of the 13 million with the diversion, you're only seeing 6 million once there begins to be any damage. So does everybody understand this first table? This is what's given in the top part of the example 1 tab. Now, there's 4 different alternatives, but for each one of these, it's just a certain size. It's the next example where we'll be considering different sized alternatives. So what we're saying is a dike of a certain size is going to perform this way. We could have built a different dike, like we could have made the walls higher, and if we built a different dike with higher walls, then that maybe wouldn't have had the $13 million worth of damage in the 5% storm. But this is just for a diversion of a certain size, a dike of a certain size, a reservoir of a certain size. And so what we're going to try and do is find out the expected annualized benefit. So we want to know which one is best. Of these 4 options, which one is best? Which one delivers on an annual basis the most benefit? So the first step is to assemble expected damage cost versus exceedance probability data, and that's given to you already. Now in the real world, this is maybe a table that you'd need to assemble, and so there would be a lot of work going into this, because what you'd need to do is you'd need to assess how each of these 4 structural measures are performing. So you'd need to find out, the dike, what properties are now going to be protected versus threatened when the dike is in place, the diversion, and so on. You'd have to essentially evaluate all of them to generate this data, and so it would not be negligible to prepare this table. But once you have it, what you can do is you can calculate the damage reduction versus this do-nothing existing alternative. So we're going to find out how much damage is avoided versus the exceedance probability. So let's actually do that. You can see step 2 in this table I've provided. We want to find the damage reduction compared to existing. Now, the existing isn't there because existing compared to itself is obviously 0. But I've given you in the dike an illustration of what the calculation is. It's the existing minus the dike for each one of these. And so this is how much damage is avoided if you do the thing. And so fill in the rest of the table. There's some blanks here for the diversion and the channel modification. But each one of them is going to be the existing versus the thing that's being compared. And so you subtract to fill in that table. Okay, so let's take a look at the channel modification. If we do channel modification, then it's going to save $6 million worth of damage during the 10% storm. During the 7% storm, it's going to save $10 million worth of damage. During the 5% storm, you're going to be saving $9 million. And so essentially by building this thing, this is money that you can consider as revenue or income, you know, an avoidance of amounts that you're going to have to pay if it occurred. So any questions with step 2? All right. Now, the incremental probability. Down here at the bottom, I explain what the incremental probability is. And so I use the illustration as the difference between the 20% and the 10% exceedance probability. Then as a fraction, that's the 20 minus the 10 divided by 100. So there's 0.1 probability between the 20% and the 10% storm. And the reason why we're calculating that is we want to find out what's the average damage reduction in that increment. And so here for the dike, what we've got is this first step is between the 20% and the 10%. And so the increment is 0.1, and then the average damage reduction that I have of 3 is the average of, there's 0 damage reduction for the 20% storm, and $6 million of damage reduction if we build the dike and if we experience the 10% storm. And so the average of that increment is 3. We're just taking the simple average there. And the size of the increment here we can say is 0.1. So I've gone through all of those calculations for the dike and kind of shown the beginning pattern for the diversion and channel modification. And so for each of those remaining blank fields, calculate the delta F for the incremental probability and the delta D. Now let me caution you that this isn't just plugging numbers into a spreadsheet template. You kind of have to really understand, it's more important to understand what it means, because you know, if you have a problem like this on the exam, you're going to be reproducing it from scratch. You may have notes on your spreadsheet that says, you know, like what these steps are, but the point is just being able to find the formula and drag the formula down through the rest of the cells isn't enough to really understand this. And so let's take a moment to make sure that it kind of makes conceptual sense. Okay, I give you down here in the bottom is the sum of delta T times delta F. And so for the dike, that column should be 0.64. See if you can figure out how to do that for the diversion, channel modification, and reservoir. What you're doing is you're summing up each of the individual delta D times delta F. Okay, calculating this is tedious, because what you have to do is you have to multiply the 3 times the 0.1 and add it to 8 times 0.3 plus 5 times 0.02, 0 times 0.03, and so on. So you have to, first of all, multiply them all together and then add it all up. And so the formula is going to look like this times that plus that times that plus this times that. So we're multiplying them together and adding them to sum it up. And then let's see, if I anchor all of the references in the A column, then I'll be able to drag the formula to the right. So let me go through and press F4 for all of the references to the A column. Okay, it's all anchored. Fingers crossed it works. All right, so 0.640 million, and we'll talk about what that is in just a minute, but to drag that sideways now, it looks like the best option is the reservoir, because you want the most damage reduction. So how much of this do you get to credit every year is what the delta F column is calculating. So in any given year, you're going to experience 10% of the $3 million savings, because that's like the size of that probability on an annual basis. And in any given year, you get to take 3% of the $8 million savings, because the $8 million savings doesn't occur every year, but we want to know the annual damage reduction. So this is going to be the annual expected benefit from the damage that is avoided. And so to annualize these, we're having to consider the incremental probability, which is the size between different storms. In the end, you can see that the one with the highest annual expected benefit is the reservoir. So this sized reservoir is going to save every year 1.378 million. Now we don't know how much this reservoir is going to cost on an annual basis. If the cost is more than $1.378 million, then you may have to reconsider whether to build it. Of course, remember that it's not always just the direct costs that should be considered, because we were talking about the direct cost of flooding, but then there's also some of those secondary effects, like the reduction in people's willingness to develop an area, the secondary damage for people who are inconvenienced when there's the damage. And so if we could somehow work those fuzzier, more difficult to quantify factors into these reductions in damage, then that may increase the savings even more. So if you lose track of how this works, I've tried to put as good an explanation as I can here at the bottom. And this is an example that comes from the textbook, though it was a rare example that I feel like the textbook really dropped the ball. It just didn't explain it in enough detail to make it clear what was happening. So are there any questions on this illustration? I think that for the homework assignment, you're doing basically the same thing. And I think that on the homework assignment, I've given you a link to a video. Is that right? Like on the equation, on the homework assignment page. Where's that? Yeah, so You may want to take a look at that video over the long run. It'd probably save you time to watch that if it's not immediately obvious what you need to do. All right, so I alluded to the fact that this is only calculating the benefits, but we also need to factor in the cost of providing certain levels of protection. So before we move on to this next example, are there any questions about this one? All right. To maximize benefit, you minimize your cost. And cost is coming from two things. The cost is coming from the damage, and it's also coming from how much you pay for a certain level of protection. And so that's the total cost. And the approach for whether to build a diversion that protects against the 5-year storm versus the 10-year storm is you add up the costs, each of these two categories, and you find whichever has the lowest. And whichever one has the lowest is also going to be the one that maximizes the annual benefit. And so the annual benefit is thought of as the savings compared to the flooding with no structural measure in place. And so the net benefit would be the difference between the reduction in damage and the cost that you're paying. And we'll look at each of these categories as we work through the next example. But before we do, consider this figure. What this is showing is, first of all, this is the damage, the curve that speaks to, for a low probability event, there's lots of flood damage cost. And for an event that happens frequently, like maybe the 2-year storm, there's less damage cost associated with that. So this curve is saying it's the costs related to flood damage. And then the other component of total costs is the cost of building things to prevent the flood damage. And so that's what this first cost curve is. And so the design level, if you're going to design against a really big storm, then your first cost is going to be high. And you can expect that the damage cost you're going to experience with a really high design level. So if you're building a really sophisticated structure that will protect against the 100-year storm, for example, now you're not having very much damage cost, but your construction costs are high. And so this total cost curve, what you should be doing is working to minimize the total cost curve, so finding the lowest point in here. It's similar to in engineering economy when you do a cost effectiveness analysis where you're trying to minimize the annual expense. You're picking how long to own something or which level of construction to do by the overall lowest cost of ownership. And so using a car as an analogy, you can buy a car that costs very little now, but then it's going to take more in maintenance and repairs as it's being used. Or you can spend more now, and there's going to be less of those maintenance and repair expenses. And so you want to balance that idea of spending a lot now and less in the future. You need to balance with structural measures. You want to balance not providing too much protection where the first costs overwhelm the damage, but trying to balance the both together to minimize the risk. Okay, now this is another example that comes from the book, but it takes a lot of staring to kind of figure out what they are talking about in this data table that's provided. And so here's how I think to interpret this table. What we have right now is a system that's providing protection against the 5-year storm. We don't have to spend anything to get the existing level of protection. But on average, right now, with the 5-year storm protection that we've got, we experience $1.94475 million of damage per year. So that is the amount of damage that comes to us from all of the storms that's larger than the 5-year storm. So remember that even if you provide protection against the 5-year storm, you're still threatened by the 10, the 25, the 50, and all of those other big ones. And so what this annual damage represents is all of the storms that are larger than the row that you're on. So if we have 5-year protection, we don't have protection against all these other storms. Now, since we already have 5-year protection, it costs you nothing to get it because it's already owned. But if you were willing to spend $0.2 million per year so that you have protection against the 10-year storm, then what that means is that now you're only exposed to damage from all of the storms bigger than the 10-year storm. So you're threatened by the 20, the 50, the 100, and so on, all the way down through the list. And so what that means is if you spend $0.2 million per year, now your annual damage is only $1.64475 million per year. So already we can tell that's a good deal because you're spending $0.2 million a year and you've just reduced your flood damage from 1.94 to 1.64. So in other words, you spent $0.2 million and then you reduce your damage by $0.3 million. And so the rule is you should always spend the additional dollar if you're saving more than you're spending. So should you spend $0.2 million to save $0.3 million? Absolutely. So keep buying the next largest alternative until the incremental cost outweighs the incremental benefit. Then you shouldn't build the next level down. So what we're going to do is we're going to analyze this situation to figure out how big should we choose. Should we choose the 10-year? Should we choose the 20-year? Should we choose the 50-year level of protection? And that example is on the second tab of the template file that I provided. And so what we're going to do is calculate the total cost, which includes both the damage and the cost of providing protection. So these two columns can be thought of as the two curves that make the total cost curve. So there's the cost of constructing the structural measure, and there's the cost of the damage. And so we want to know the total cost by adding these two columns together for each year. And then the benefit is going to be the reduced damage compared to the existing protection. And then we also want to do the net benefit. All right, so that is here on the example 2. So the total cost you can see is the damage and the annual cost together. So we'll calculate that column down. The benefit is the difference between the annual damage from the existing condition and the annual damage of the row that you're on. And then the net benefit is the annual benefit minus the annual cost. So, how big should we build this, what was it again? It's a dike system. Well, if we want to maximize the benefit, that tells us that if we build protection against the 50-year storm, then that's going to minimize the damage. Compared to every year having $1.94 million worth of damage, we're only going to have $1.649 million worth of damage. And to get that big reduction in damage, we only have to spend $1 million per year to do it. And so the total cost, where you're adding together the damage expense and the annual expense of having that dike system in place, you're going to have to pay something. You can either pay for the flooding, you can pay for a dike, or some combination of the two. But this is the one that has the minimum cost for each year.
This is only direct cost, right? It's not really looking at direct cost.
It depends on what's going into these damage estimates. I mean, in this example, it doesn't really specify in the book, but let's just pretend that it's including the direct and indirect costs. And that those have been realistic estimates, because you can goose the numbers any way you want. Like if you say that it's worth $1,000 an hour not to have to shovel mud out of your front driveway, then, then it's going to seem like you should build the biggest dike in the world. But, Here, the biggest differential between the cost and the damage reduction also corresponds to the largest net benefit. So the net benefit is saying the difference between the benefit and the costs. And so it's like you're, compared to the baseline situation, you're coming out $295,000 per year ahead, because this is in millions. So if you find someone to finance this for you, like a bank, or you can take out bonds to build the structural measure, then it's essentially free money. Then you're saving $295,000. Now the other thing to keep in mind is that the people who are threatened by flooding may not be the same ones that are being asked to pay for the cost of the structural measure. So if you live up on a hillside in a town and the people who live in the low-lying areas are trying to get everyone to chip in equally, then that's a bad deal for you because you're not going to be enjoying the direct benefits of the flood reduction. But you know, there are all those secondary factors where if you can't drive through the roads and if your grocery store is underwater and your employer is underwater, the fact that your house isn't directly in the floodplain is great, but it's not like you've avoided all of the damage altogether.